We're going to start our first unit in the kinetics equilibrium unit, which is on kinetics. And you see this nice, fun math equation right here. It says later in the 50s, I got involved in the kinetic studies using my long forgotten, oh no, math background. So, the first thing we want to realize is that you should understand the factors that affect the rates of a reaction. Okay, if you have a reaction, it's not going to be a consistent linear trend. Instead, it's going to exist as kind of a curve this way or a curve this way, depending on what you're looking at. We want you to be able to predict the rate of reaction from a concentration, and we want you to be able to classify something as a zero, first, or second order reaction. So, kinetics is a study of how fast reactions happen. Not only how fast they happen, but how they react. So you can determine the speed of a reaction. Now, here's the reason why. Okay, TNT has less energy released than a cookie on a per gram basis. 1 gram of TNT and 1 gram of a cookie, the cookie wins. The reason why TNT is bad is because it releases that energy very quickly, whereas a cookie releases that energy very, very slowly. So the kinetics of the reaction, how quickly the reaction can make the difference between whoops and yay. So the physical states of the reactant will help determine what's going on. Solids are generally not considered to be reactive because it is very difficult to have solid particles interact with solid particles. Aqueous are generally considered to be reactive, liquid are generally reactive, and gases are the most reactive. So the physical state of the reactant will help determine the speed at which the reaction occurs. Okay, the mixtures, a homogeneous mixture is considered to react more quickly than a heterogeneous mixture. And the reason for that is, and if you have a heterogeneous mixture, the only interaction that can occur is at the barrier. So these molecules can interact right here, whereas when you have a homogeneous mixture, there's closer proximity between all of them and they can react all over the place. So the physically closer the reactants are, the more likely they are to react. So the physical state determines it, but also the density of it will affect the speed of the reaction. These molecules right here are much more likely to interact than these are because remember, you have to have an interaction between the molecules in order for a reaction to occur. On this right side, the only two are right there, whereas here, almost all of these can have some sort of interaction with one another. Okay, a lot of times we look at a reaction on what's called the collision model. Two molecules have to collide in order for a reaction to occur, and that only happens if they are in close proximity. Another factor that determines the kinetics of a particular reaction would be the temperature. Now, the temperature means that the molecules are moving faster. Whenever the molecules are moving faster, they have more energy. Whenever they have more energy, they're going to collide with greater energy. They're going to collide more often, and you have to overcome what's called the energy of activation barrier. So, this right here is the energy they have to collide with. Well, if molecules are moving more quickly, then now all of a sudden, instead of having to go from here to the top of the curve, they're trying to go from here to the top of the curve, and it's much an easier jump for them. So, temperature, generally increasing the temperature will increase the rate of a reaction. A catalyst will increase the rate of reaction. So what catalysts will do is they'll bond to one or more of the reactants. Usually it's both of them. And what happens is a reactant will come in here and a reactant will come in here. And now they're close enough where they can physically react with one another and then be released. Now a catalyst is unchanged in a reaction. Now the reason why it changes the activation energy is it bonds with one thing and then bonds with another, so it makes it much more likely that these things are going to be able to interact. It does speed the reaction up, it does put the reactants in close proximity with one another, and it must remain unchanged. A lot of times when you think of catalysts, you think of enzymes from biology. Now, those enzymes are very, very efficient catalysts, but they're not actually what we're talking about here. When we're talking about catalysts in chemistry, we're talking about things like platinum. Platinum is a great catalyst because it does allow things to connect relatively quickly, but it is very, very unreactive. An inhibitor is something that will bond to one or more of the reactants. If it bonds to one of the reactant, it prevents the second substance from interacting with the first. So inhibitors remain bonded to one of them and prevent the interaction from occurring. What an inhibitor will do is it will bring a reaction to a stop. Okay, that right there is what an inhibitor will do. Now, whenever you're measuring the rate of a reaction, in other words, how fast a reaction is occurring, you actually have a choice. You can look at how quickly product disappears, or you can look at how fast, or how fast reactants disappear, or how quickly products form. Because those rates are tied to one another by stoichiometry. You can use the balanced chemical equation to figure out the second if you know what the first is. So, when we look at reaction concentration, the first thing we want to do is we look at our balanced chemical equation. We do have a balanced chemical equation right there, and what that is that's 1 chlorobutane. And if you were to look at our table that we have here, the concentration of 1 chlorobutane it decreases with each time period to the point where we get to 0. So whenever it decreases, the butanol and hydrochloric acid must increase, because if this is our reaction, if this goes down, it has to be because we're making this stuff right here. So these things have to go up. So we can look at reaction concentrations, and we can use stoichiometry. So if I wanted to know how much HCl there is at 50 seconds, or what the molarity is, what I can do is I can say, okay, well, this right here is how much disappeared. I originally had a molarity of this at this point, and then now at 50. So I had 0.095 molarity of this disappear. Now you look at the stoichiometry. You say if I have 0.09095 molarity of CH4Cl, well, C4H9Cl, for every 1 mole of this, I produce 1 mole of HCl. So because of that, for every 0.095 of this to disappear, 0.095 of HCl should appear. So now, this question says, what is the state of the product of the chemical reaction below? And so if you were to look at this thing, you could say that it does have to be in a gas right here, because we're talking about pressure. Pressure is the only one in which you can change the pressure. What it's saying is that we have some sort of reaction, and as that reaction occurs, it is producing a gas. Gas is the only one that would increase the pressure. If you actually had a solid or a liquid produced, it would have no effect on the pressure whatsoever. Next, it says, what is the average rate of formation for D if the concentration of A is shown below? So this right here is the concentration of A, and it says, okay, I want to know for the first 9 seconds. So that means I'm going to look at this term and this term right here. So now when you do this, you have to figure out by how much A decreases. And so I would say 0.906 minus 0.562. And then you would use your calculator and you'd say, okay, that means this is 9, and this is, well, I don't need to do that. So that's 4, and that's 10, so 4 and 0, or 4. So you have about 0.44 is going to be approximately the change right there. So this right here represents the decrease in A's concentration. So now you need to look at by how much the increase of D is going to be. So when you look at the stoichiometry of this thing, you would say for every A that disappears, you create 3D. So I would say 0.44 is the change in molarity for A. For every 1 mole of A, you produce 3 moles of D. So when you multiply this out, you'd say 0.444 times 3, and that would be your answer. Next, we can look at reaction rates, and we can say, okay, if you look at the reaction rates, they're not consistent. They're not the same thing over time. In other words, you can't say, oh, look, it's this nice pretty graph. It's a constant velocity graph from physics. It's not that easy. Instead, what you see is you see that the reaction rate changes over time. And because the reaction rate changes over time, you create something that's more of a curve. And you should know that if you're starting to talk about curves and things like that, that's when calculus starts to come into play. Now, if you notice, it doesn't actually curve up like this. Instead, the reaction rates curve down so that you have an initial reaction rate that is very fast, and then it slows down to where the reaction almost comes to a stop. Now, you can actually express this as the change in concentration over time. That's what we call the reaction rate. So the reaction rate that we have here, it says it changes over time, and so you see 2 distinct graphs right here. This graph right here, okay, it says the concentration in moles, and that represents you're increasing the concentration of moles, so this would be the products. Now if you look, the products tend to be increased very quickly at the beginning and then they fall off. This right here represents the reactants. And if you look, the concentration of the reactants initially drops off very quickly and then it levels out as well. So this right here is considered to be the reaction between the products of the reactants. This is generally considered to be an equilibrium position. Now, it doesn't mean that every one of these is equal or that it will stay there, but that's an interesting point whenever you have the molarity or the concentration of the products and the concentration of the reactants be equal. Okay, so when you have this equation right here, the less interaction between reactants as the reactants proceed. So for example, if these are all my reactants, they can react with each other all over the place because they're in close proximity to one another. They can collide relatively easily. But as you start to make product, there starts to be things in the way that prevents the reactions from occurring. So as you proceed from step to step, there is less interaction between the reactants. So because of that, there is less reactions. Okay, the reaction rates are continually changing. Because they're continually changing, you have to use calculus or integration or differentiation whenever you're looking at these particular rate laws. Now, you will not have to use calculus. Okay, calculus is where the laws come from. Okay, but I will give you the laws and you can look at them and just say, okay, yeah, that's what it is. You don't actually have to generate the formulas themselves. Okay, as you do this, the reaction will slow over time as the reactants decrease. So the reaction rate usually refers to the initial rate of concentration. So whenever I say the reaction rate is, it's generally referring to this initial reaction rate. Okay, and most of the time it tries to specify, it says the initial reaction rate is. Okay, so now this is an example. It says sketch a graph of concentration versus time for the reaction below. So if you were to look at this, okay, we can say we've got time and we've got concentration, and we're going to go ahead and do concentration of all of them. The first one we're going to do is we're going to say A. So as time goes, you're going to have less A and you're going to have a more difficult time interacting. Okay, so actually that's not right. You're going to start off with a lot of A and it's going to slowly go and asymptote out. The same thing is going to occur for B. You're going to have a certain amount and it's going to plateau out. If you were to look at the concentration of C, it is going to increase. Now the slopes are not necessarily going to be the same here. The slope here is going to be twice the slope here, because for every one A that disappears, you're going to produce 2 of the C's. So this is going to have a much higher initial slope. Okay, the next one says 20 grams of copper will react with excess silver nitrate in solution. After 10 seconds, an inhibitor is reduced, halting the reaction. So the reaction is done after 0 to 10 seconds. This is the mass of copper is measured to be 0.8. What is the rate of formation of silver? So if we were to look at this thing, we have to start with a balanced chemical equation. We have copper plus silver nitrate, and we're going to say that it goes to, we'll say it goes to copper 2 nitrate. We'll say the oxidative state is 2 plus silver. Okay, so once we do that, we say, okay, I've got my balanced chemical equation. I got to put a 2 here. It says 20 grams of copper is reacted after waiting 10 seconds. What's the mass? Oh, we also need to put a 2 here. What is the rate of formation of silver? So I can look and I can say, okay, I had 1.2 grams of copper actually react. I can use the molar mass of copper of 63.5 grams to say that's how many moles of copper reacted. Now that is in 10 seconds. So once you do that, you know how many moles of copper reacted. But for every 1 mole of copper that reacts, you have 2 moles of silver that react. So you need to be able to take this and multiply it out, and that will give you the average moles of formation that form every second. So now when we look at concentrations and the rate of reaction, so what you see here is a reaction of ammonium and nitrite, and it's going to make nitrogen gas and water. So the first thing it'll do is it'll give you several different experiments, and those several different experiments will vary the concentration of each one of the reactants to begin with and see what their effect on the initial rate of reaction is. This is a very common experimental setup for an AP question, so you need to get used to seeing tabular data like this. When you do, it's best to compare experiments that are when you have constants and variables. So if you look, for the first few experiments, these values, the concentration of the nitrite is a constant. So the influence on the particular reaction is going to be solely due to the ammonium ion. Now when you look at it, for experiments 1 and 2, you see you double the concentration of ammonium, and the resulting initial rate of reaction doubles as well. And you see it again, you double it between 2 and 3, and you double the rate of reaction again. Okay, and then right here you can see that there's another increase, but it's not by a factor of 2, so you don't see an increase by a factor of 2 here. What that allows us to do is say that when the NH4 doubles, the initial rate of reaction doubles as well. So when you compare reactions 5 and 6, if you look at 5 and 6, you are maintaining the ammonium as a constant. Whenever you maintain the ammonium as a constant and you double the concentration that you have of the nitrite, you likewise see a doubling of the initial rate of reaction. So what you can say is that this particular reaction does depend on the concentration of ammonium, and it does depend on the concentration of nitrite, which does make sense when you look at the equation. So the rate of reaction is proportional to this, which means if you double this, you double this. The rate of reaction is proportional to nitrite, because if you double nitrite, you double the rate of reaction. So a lot of times what you'll do is you'll say, okay, well the rate is proportional to both of them. Okay, if you double one term, you double all of them. Now a more common way of saying this is saying that rate equals K, where K is some sort of rate constant times the concentration of the reactants. Now, this turns the proportionality that you have here into an equality. So instead of just saying they double, you can actually figure out exact values for the rate of reaction. Now, whenever you look at a rate law, the rate law shows the relationship between the reaction rate and the concentration. So you have something like rate is equal to K, and then you have usually A and then B. Okay, that's an example of a rate law. Now you can have exponents that are involved here. Okay, for example, you could have a 1 here and a 2 here. Okay, how you would figure out if there was a 1 or a 2 there, you would look at the initial data. Say, for example, that you doubled the concentration here, and this increased by a factor of 4, and that you tripled this here, and this increased by a factor of 9. What that would mean is that this would no longer be a 1, but instead would be a 2. So that's how you determine the exponents that are associated there. But when you look at the overall reaction, you can say that this is a first order reaction with NH4. The reason why is if you double the NH4, you double the rate of reaction. It is a first order reaction for NO2 because when you doubled NO2, you got that. So we're left here with rate is equal to K, and then you have NH4 plus, and then this is a 1, or generally speaking, we're not going to put it, NO2 minus, and then this is also a 1, and generally we won't put that there. So this implies that it is a first order reaction for both of these. But if I want to look at the overall rate of reaction, the overall rate of reaction is a second order because I have a 1 and a 1. Whenever you look at the overall reaction order is by adding the exponents together. So you take 1 plus 1 is 2, which means this is a second overall order reaction, which means it's going to have a little different properties than if it just depended on one thing on its own. So we need to get to something called integrated rate laws. Now, when you look at integrated rate laws, we're going to use calculus to integrate the rate laws for a first order reaction. So now when you do this, realize that there is no calculus in this class. Okay, I'm going to show how the calculus actually works real briefly, just for people who have taken calculus before. Okay, generally speaking, you're going to have what we have here. Rate is equal to K, and then you have the concentrations that are associated with that. Okay, now remember, you also have the expression that we said before, the concentration of A. Okay, so you have a change in the concentration of A over time. Okay, that's one of the things that we said before was the rate law. Okay, it's telling you how quickly this concentration of A changes. And this right here is an example of the rate law, which can equal this particular term right here. So if you were to take this term right here and you were to integrate it, when you integrate it with respect to time, because time is your dt value, this is the value we end up with. Because when you do, there's an identity that says when you integrate this change in A over time, you end up getting with delta T, or excuse me, the concentration of AT over the initial concentration, the natural log. Do you need to know any of that? Do you need to know that integrate? No, you don't need anything to do with this. Okay, I'm just trying to show the origin of where it comes from. Okay, what you do need to know is this. Generally speaking, we will linearize these equations, which means we will set them up so that they are a straight line. Okay, so for example, if you were to take this right here and try and make it into a straight line, what you would have to do is you'd have to say, okay, there's an identity that says that when you take two natural logarithms and divide them, it is the same thing as subtracting them. Okay, that's an identity. So what you end up with is this particular line right here. Okay, if you were to add the initial rate of concentration, this right here is a linearized version of the equation. Okay, you have your y, which is the concentration at any time, which is the dependent variable. You have your minus kt, where k is the slope, which is going to depend on the factors associated with the equation. You have time, which is going to be our independent variable. As the time is allowed to proceed, you're going to have a changing rate of concentration. And then you have the B value, which is your initial concentration. Okay, that's where it's going to cross the x-axis. So if you were to look at it, we have an interesting graph. We'd have time, and we'd have the natural log of A on this axis, where we'd have a y-intercept of the natural log of A sub 0, and then you'd have an interesting line going down. Now the reason why the line's going to go down is because you have a negative value for kT. Because in other words, you're going to lose concentration as the reaction proceeds forward. Okay, so what this means, if you have a first order process, okay, so for example, if I have something like rate equals A, and that's it. That's a first order process because this is a 1. The equation will be linearized whenever you graph this. So if you create a graph, it ends up looking like this when it's the natural logarithm. Okay, a lot of times these are multiple choice questions on the AP test where they will give you graphs like this and they will change these axes and they will say which one of these represents a first order reaction. And you've got to say, okay, first order, that's the natural log. Once I have the natural log, that's got to be it. Okay, now the reason we said it's a negative slope is because remember that negative K value, the fact that you're going to lose concentration as the reaction proceeds forward. Okay, so a first order process, an example of this is when you have methyl isonitrile. Okay, so that's that fancy name for CH3NC. Whenever you take this thing, it can convert into CH3CN. Okay, now if you look, this is exactly the same number of atoms, just rearranged differently. So because of that, this is considered to be a first order process. It's an atom acting on its own. It's not doing anything, it's reacting with itself. It's only going to depend on the concentration that you have here. So because of that, that's a first order process. So whenever you do this, this is the sort of data that you would collect experimentally. So you'd have pressure, and pressure is the gas equivalent of concentration. Okay, if you have a certain concentration, that's going to indicate that it's some sort of solid or some sort of aqueous product. If you have the pressure is going to indicate that it's some sort of gaseous product. And if you look, you can see the pressure of CH3NC. It's going down as you proceed forward. Okay, if you look, it has a continually changing slope. Because it has a continually changing slope, we know we're going to have to look at it in terms of our natural logarithm graph. Okay, if you were to take the natural logarithm of each one of these values, these points, you can then plot those points, taking the natural log of all those points, and plot them over here, and you end up getting values that plot linearly. Okay, whenever you take the natural log, you get a straight line. Because when you take the natural log, you get a straight line, you can say that it is a first order process. Not only can you say that it's a first order process, now that it is a straight line, you can easily calculate the slope. The slope is going to be the k, or the rate of reaction for this particular set of data. Okay, it is very, very hard to get the k value if you're not given some sort of tabular data or some sort of graph. So you will always be given a graph or some sort of table from which to find the k value. The k value is going to be different for every reaction. You can't be expected to look them up on a table or memorize them. Next, we have second order processes. So whenever you have a second order process, it's not the same as a first order process. It depends on more than one thing. Our initial example that we said, rate is equal to, and then we had two things. We had the concentration of NH4 and NO2. Now this right here is a second order process because it depends on two factors. So whenever we do this, we can have to put it together into a combined rate law, but generally speaking, that's not going to work. You have to set it together as a second order reaction. So we're going to say rate, and then we're going to say it's a second order. Now, what differentiates a second order process from a first order process is how quickly the reaction is going to be done. Okay, so what we're going to do is we're going to still have a graph of our original data. But whenever we do the natural logarithm in the time, it ends up still not being straight. So it's not linear. Whenever we say it's not linear, we can say it's not a first order reaction. So now we proceed and we say, okay, well maybe it's a second order reaction. The second order reaction, instead of having the natural logarithm, instead it has 1 over a minus kt. Notice how that's still the same term, and then plus 1 over a. Okay, so whenever we do that, we get a second order process. So if you were given a graph on the AP exam and it says 1 over delta A and then time, and there's a straight line, you can now say that this is no longer first order. Okay, it's second order. So you have to pay really close attention to what is on the axis, because if you have two identical graphs and the AP test says, okay, well, which one of these is the correct value, you need to say, okay, what is the reaction? Is it first order or second order? And then you look at the graph and say, okay, well, it's first order. Okay, well, it's second order. So you have to pay really close attention to what's on the x and y axis. Okay, next, it says a second order process, and this gives you an example of it. Okay, this right here says it's the decomposition of NO2 at 300 degrees Celsius. Now, this is a good example of a second order process because it's a single molecule that depends on two factors. So whenever you do this, you can't have this particular reaction proceed on its own because you would have one half of an O2 molecule, which doesn't make any sense. So instead, you would expect two NO2 molecules to react together. So in order for this reaction to proceed, you would expect the reaction to have to happen twice. Okay, so when you look at the data, you see the original data right here, you see it's changing, and then you would plot the data. Okay, whenever you plot the data, you're going to get a curve that looks just like we're getting used to. And whenever you plot that particular data, you say, okay, the first thing that I'm going to do is I'm going to take the natural log of all those values. When I take the natural log of all those values, these are the values you get, and it still represents a curve. It's not straight. Okay, please don't try and take these values and say, oh, well, it's pretty straight. I can draw a straight line that's pretty close. You should very clearly see that they have a constant slope or they do not have a constant slope. In this particular case, because it is not a constant slope, it is not first order. So we proceed to the next thing. We say, okay, now I go 1 over, 1 over, 1 over, 1 over, 1 over, 1 over, and you plot the data. Whenever you plot the data, you end up getting a straight line. So because of this, we can say that there's a straight line, and this has to be a second order process. Half-life is a very specific rate reaction law, and it's actually pretty useful because it's very easy to work with. And the reason why is because you can set up your rate of reaction very easily. Because half-life is defined as the time that it takes to half the concentration or half the amount, it's very easy to set up an equation that you have concentration is equal to zero point 0.5 of the initial concentration. So that's what we call a half-life expression for concentration. If you were to take this and then integrate it, what you end up with is you get this value of the natural log of 0.5 A0 divided by A0. And that's the integration. We don't need to know any of that. But very specifically, when you look at it, these things somewhat cancel out. So when you get this, these cross out, and you end up with a natural log of 0.5. Well, the natural log of zero point 0.5 can be plugged into a calculator, which is minus 0.639. And that equals minus kT. Now, whenever you're dealing with half-life, you specifically say t to the 1/2, because that defines the time that it takes to reduce it by half. So whenever you rearrange this equation, you actually get the expression that says 0.639 divided by k is equal to the half-life expression. So this is what we call a first-order half-life that does not depend on the initial concentration. So examples of these things would be like radioactive isotopes. Okay, they tend to degenerate or fall apart on their own, and it doesn't depend on how many there are. Now, there are certain half-life expressions that do depend on the concentration, but we're not going to look at those. Okay, so now generally speaking, that has to do with the rate laws. Generally speaking, we look at the half-life, we looked at the first order, and we look at the second order. Now we're going to look at some factors that affect the rate of reaction again. So generally, temperature increases, so does the reaction rate. That's because K is a temperature-dependent quantity. Okay, as you increase the temperature, the K value tends to increase as well, and it has to do with the movement and the activation energy and how much energy is associated with the molecules and what their orientation is. So because of that, as temperature goes up, the K value goes up. Now, generally speaking, when we look at why reactions occur, one way that we know that reactions occur is according to the collision model. Now, the collision model is a somewhat simplistic way of looking at it, but it basically says molecules can only react when they collide with each other. So, for example, if I have a molecule that looks like this, X, Y, Z, the only way that A can come in and react is number one, if it collides with the molecule, and number two, if it collides with the molecule in the correct spot. For example, if A collides here, there will be no reaction. If it collides here, there will be no reaction. If it collides here, there will be no reaction. So because of that, the collision model is specifying that the chemical reaction occurs whenever they collide with the correct orientation and the correct energy. So you see that here. You see before the collision and then after the collision. Now, if this green ball were to interact with the red or the blue, you would not have the same interaction. There could be a different reaction, or there could be no reaction. So, the activation energy, or the energy that's associated with the reaction, has to be overcome in order for the reaction to occur. And you see that on the graph. So you see our initial energy of our atoms. We see our energy right here. So the energy is lower than the initial reaction, so we would say that's an exothermic reaction. As a review, we'd say it's exothermic. But you have to have this initial increase in energy. Now, this initial increase in energy is called the activation energy. Now, the activation energy will lead to what's called an an activated complex. Now, the activated complex is kind of what's called a transition state. So it's a point between the reactants and the products where everything's kind of jumbled up with temporary attractions and bonds, and it is not a stable state. Because it is not stable, it requires a lot of energy to reach that state. So that's why you have this initial hill right here that you've got to overcome. So this is what you see here. You see the change in energy. The high point is called the transition state, and then whenever these things are together, it's called an activated complex. And so as the molecule, you have your initial molecules, as they start to rearrange themselves and then collide, you see it's in a very, very unenergetic state. You see this particular molecule right here is connected to 1, 2, 3, and then it forms in the middle of the bonds there. Then it correctly starts to orient itself, and after it orients itself, This is the lowest possible energy state that we're used to dealing with. So now we need to review the Maxwell-Boltzmann distribution. Remember, the Maxwell-Boltzmann distribution is generally used to talk about the number of molecules and how fast they are moving, and it's a statistical distribution. So whenever you see this, as you increase the temperature, you decrease the number of molecules that have kinetic energy because you're stretching this out. Now, as you increase the temperature, you increase the fraction of molecules that have enough energy in order to overcome that energy barrier. So you see the curve flattens and broadens, so the higher the temperature, the more likely it is to react. Okay. Now the dotted line here represents the activation energy, so you see that, like we said, the reaction rate increases. Okay. Now, one of the things that you do need to be aware of is this particular formula right here. Okay. This particular formula represents the frequency or the fraction of molecules that will have enough energy to overcome the energy barrier. It can be calculated using this formula where E stands for the 2.7e. The E on your calculator that looks like this. It's the opposite of a natural logarithm. Okay? And then this right here is the activation energy. How much energy is required to do the experiment on a per mole basis. Then you have the gas law constant, which you're talking about your 8.314, and then you have the temperature in Kelvin. Now, Arrhenius actually developed, he did more than just acids. He developed this mathematical equation between K and the activation energy. And you will see this Arrhenius equation. But basically what it's saying is that the constant depends on the activation energy, the gas law constant, and the temperature. So this is what we call the frequency factor. It depends on how much is actually the likelihood of the collisions actually occurring. So this A term is something, it's a constant that has to be determined for each reaction. Okay, so now we need to talk about the idea of reaction mechanisms. So reactions happen in more than one way, and so we need to know if they happen in more than one step, what step is the one that determines whether or not the reaction will actually occur. So whenever you look at these, so you have all at once or several steps. Now we're going to assume that they occur in a couple of different steps. So each process within it is going to be known as an elementary reaction or an elementary process. So it generally just doesn't go from A to B to C. It goes from A to A prime, and then A prime plus B is AB, and then AB goes to AB, which goes to C. So this right here could represent a stepwise of very different elementary reactions that represent the overall reaction is just A plus B goes to C. Now each one of these processes may be very, very fast or very, very slow, and that will depend, or that will determine whether this reaction occurs fast or slow. So you see reaction mechanisms. So whenever you have a unimolecular reaction mechanism, you see it right here. A goes to the products. You have your rate law. Okay, so whenever you look at these reaction mechanisms, it will determine whether it's a fast or a slow process. You can actually name these things: unimolecular, bimolecular, teramolecular, all those sorts of things. That is determined by how many reactants there are. Whenever you have a multi-step mechanism, one of the steps is slower than all of them. That particular step is called the rate determining step. Whenever you have multi-step mechanisms, the slowest one determines the speed. Okay, you can't go faster than the slowest step. So if you think about it, if you're stuck in traffic and you're on a one-lane road, there's one car, you can't go faster than the slowest car. It's the same way when you have reactions. Okay, you can't go faster than the slowest one. So whenever you have a slow initial step, this is an example of it. The rate law is found experimentally to be this. So whenever you have this particular rate law, the CO is necessary for this reaction to occur, but the rate of reaction does not depend on it. The reason why is the formation of CO occurs very, very quickly. And so because of that, it occurs quickly compared to this particular step. And so this right here indicates that it's going to be a two-step reaction. So when you look at this, you have a slow step initial. So NO2 plus NO2 goes to NO3 and NO. That would be a very slow process. The reason why is these are more stable, okay, than the products. These are much, much, much higher in energy. Okay, the reason why is it's going to violate all sorts of rules in terms of the octet rule, the number of bonds, valence electrons. It's just not going to be stable structures. They're going to be high in energy. So because of that, that's going to be a very slow step. Now, whenever you have this unstable product from the first reaction, it does not want to continue to exist in a high energy state. So what you can say is that these two factors right here are more stable, and so because of that, it's going to be a very, very fast reaction. So the intermediate, this NO3 that you originally see, is consumed in the second step, and so it's gone very, very, very quickly. Okay, so CO is not really involved in the slow determining step, so it doesn't appear in the rate law. The only thing that appear in the rate law are the ones in the slow step. So if you have a rate law and it's not in the rate law, then it's in the fast part of the reaction. That's how you identify whether it's a fast or a slow. If it's not in the rate law, it's a fast step. If it's in the rate law, it's a slow step. Whenever you have a fast initial step, you see that the rate law has nothing to do with those particular factors. So if you look at this, it suggests that you have a multi-step reaction here. So when you look at it, the fast initial step says you have NO plus Br2 goes to NOBr2. Now that's going to occur very, very quickly, but then once you do that, the interaction of NOBr2 with NO is very slow. Now step 1 includes the forward and reverse reaction. Whenever you have something occur quickly, it's going to occur quickly, and then it's going to move back quickly. Then it's going to move quickly, and then it's going to move back quickly. So this is going to be a continually changing concentration. And so this continually changing concentration is going to affect the slow step. So when you have a fast initial step, the rate of the overall reaction is going to depend on the slow rate, but then the slow rate also depends on the fast initial step. So whenever you look at this thing, this right here is our overall rate of reaction, but this right here depends on the first step. So in order to find the concentration of NOBr2, we need to find something to substitute in there. Well, whenever you look at this, our initial step says NOBr2 can react in two ways, with NO to form NOBr, or by decomposition to get this. Well, the reactants and the products of the first step are in equilibrium, which means whenever you have something in equilibrium, the rate of formation is equal to the rate of the reverse reaction. So if you were to look at it from that context, you can actually plug something in there. So you have the initial rate of reaction, so this is the rate of formation, and then this right here is the opposite of those. So we can say those two things are equal. Well, whenever you do this, you can actually solve this step for the concentration. Whenever you solve this step for the concentration, you actually end up with this value right here. So whenever you take those things and you substitute them in, you now have this is your overall rate law. So you have your first step right here, you have your second step, which you plugged it into, and then these three constants are multiplied together to find your overall rate of reaction. Whenever you have a catalyst will increase the rate of reaction by decreasing the activation energy. Generally speaking, the reason why catalysts do that is they actually arrange the molecules in a certain way to lower or to fix the orientation so the molecules will be properly aligned, so that it will overall decrease the or increase the likelihood that they'll be oriented with the proper energy. Now, if you notice, it also has kind of a peak to collide with the catalyst, and then it overcomes an energy barrier. But overall, that energy barrier is much less than the initial energy barrier. So, one way that a catalyst will speed a reaction is by holding the reactants together until they have the ability to react. So, if you're talking about two molecules in free space, they're not going to be next to each other very long, so the reaction must be very quick. Now, if you were to take this and it was to hold something, it was to hold this molecule there until something comes along and reacts with it, that's how most catalysts work, especially something like platinum, which is what you see here. Now, an enzyme is a very specific type of catalyst for a biological system. We've already talked about that. It connects, and whenever it connects, it allows those two things to react and connect or tear apart, as you see here with a decomposition reaction. Now, at this point, if you're still having problems with kinetics, and you most likely are, realize that this is a very, very difficult subject on the AP test. It's the one that you really have to spend some time with. Almost everything else generally will come to you at some point. This is one that you're going to have to look at the video. You're going to have to pay attention in class as we go over each particular practice problem. You're going to have to read the chapter as well, and you're going to have to come ready to ask a lot of questions in class because this really is a difficult concept to understand. In fact, this is probably the most difficult chapter that we will cover this year.